At the start of Chapter 7, we really began to fiddle around with exponents in order to change numbers so that they might be easier to deal with when we face them in a problem. A fundamental example would be evaluating 4 to the 5 halves power. And one way that we approached it was to actually break down the 4. So to break down the base, and then to handle the exponent second. So one way we went about it was factoring 4. 4, of course, is a nice number, in which we factored into 2 squared. So we can easily replace 4 with 2 squared to the 5 halves power. And what happens when I have a power raised to a power is I actually multiply. So 2 times 5 halves, the 2's end up dropping out, and you just get 2 to the 5th. You keep your base, and then the power you ended up with after the multiplication. So 2 to the 5th, and so your final answer would be 32 when you evaluate 4 to the 5 halves. And that's a very simple example of what we've been attempting to do. In 7.2, we learned some more properties that are going to allow us to handle these exponents a little bit better. The first 2 rules that we learned were the product and quotient rule. So that means if I have a base or an index number, let's go ahead and say it's the cube root. If I have the cube root of a number, and let's go ahead and say it is 27. Well, the product rule tells me that I can break 27 apart into any product. I can break this number into factors. So let's just say 3 times 9. I can break it apart into 3 times 9. So that would mean I have the cube root of 3 times the cube root of 9. And the product rule going this way and going backwards is going to help us simplify numbers and get rid of some radicals if possible. The quotient rule is relatively similar. Since I went forwards for this one, I'll go backwards for the quotient rule. So the quotient rule has, I'll do the 5th root. The 5th root of 64 over the 5th root of 2. So if I have, for all of these rules, what I need to see is that the index number is the same. In order for me to utilize these rules properly, the index number has to be the same. So the quotient rule says that I am dividing, and if the root is the same, that means I can combine the radicals and make the division problem underneath of one radical. So then I should be able to take the 5th root of 64 divided by 2 is 32, and the 5th root of 32 is 2. And of course you could go through the steps and factor 32 and find that it is 2 to the 5th. If you're taking the 5th root, that means that 2 to the 5th is to the 1/5 power, because that index number goes in the denominator. And so then that gives you 2 to the 5th times 1/5, which is 2 to the 1st, which is just 2. Alright, now on to the multiplication and division. So a couple of simple examples here. If I have x squared times x cubed, what do we do with the exponents? We just add them. So in a multiplication problem, you should just be adding the exponents, so that would give me x to the 5th. If I have x to the 5th divided by, so here's division, divided by x cubed, you end up subtracting, so x to the 5th minus 3 equals x squared. Alright, so we're going to be utilizing all of those properties, as well as if you have a power raised to a power. This is a little bit different. This is multiplication if you actually write it out, x squared times x squared times x squared, or x to the 2 times 3, x to the 6th. And what happens when I have, let's say, 2 to the negative second? A negative exponent, this was an important note that I told you guys to write down. A negative exponent means that I can flip the position. So this really means 1 over 2 squared. And if that 2 to the negative second was in bottom, so this one, let me finish out that example, would be 1/4. If I already had 1 over 2 to the negative second, that means the negative exponent would push it up top. So that would be 2 to the negative second, or sorry, that would become 2 to the second when that brings it out of the denominator. Let me go ahead and put a 7 here. So that 2 squared is going to end up multiplying by 7. So you get 4 times 7, which is 28. And this is just a review of a couple of the rules that we have in the charts at the start of 7.2. Rationalizing the denominator is something I did not go into depth with when we were covering this section. However, this is very important, so when I repeat it in class that it would be important to watch this video. This right here, rationalizing the denominator, is what you guys need to take a note on. So rationalizing the denominator, so that means when I have I don't know, let's pick an example here. 5th root of 5 over the 5th root of 27. When a problem says simplify this expression, use the properties, whatever, we somehow need to mess around with it so that it is simplified. And mathematicians, one of the rules why we rationalize the denominator is we don't like radicals in the denominator. We do not like radicals in the denominator. This is a special note. So how can we get the radical out of the denominator? This is the big question. Now, I'm not 100% sure of why we don't like the radicals, but we like to make sure that there is one radical in a problem because it's going to make it easier to handle and also to type into a calculator. So let me go ahead and break down 27 into its factors, just so this might be easier to see. So 5th root of 5 and 5th root of 27, which then gets replaced with 3 cubed. Rationalizing the denominator means that I am getting the radical, in this case the 5th root, out from underneath the denominator, and somehow I'm going to be able to put it up top with that 5. So the question here is, in order to get rid of a 5th root, I need to take a 5th root of something. Well, I only have 3 cubed here. So in order to take the 5th root, I need, as far as I know, 2 more 3s. I need to be multiplying 2 more 3s so that I would be able to have 3 to the 5th and take the 5th root. So I need 2 more 3s. So I'm going to go ahead and say 9 here. I need a 9. And in order for me to use the product rule, it needs to have the same index number. So that index number needs to match, which if I take the 5th root, it is going to. And the identity property of multiplication tells me that if I have the 5th root of 9 over the 5th root of 9, I'm really just multiplying by 1. So I'm not doing anything too funny and not anything illegal. So what happens in the bottom? If I have the 5th root of 3 to the 3rd and the 5th root of 9, which is 3 to the second, fifth root of 5 times the fifth root of 9. The reverse product rule tells me that I can go ahead, since all of these index numbers are the same on top, I can go ahead and do 5 times 9, which is the fifth root of 45. And on bottom, I'm going to end up with the fifth root of 3 to the fifth. And that conveniently reduces to 3. So here's your solution. That is rationalizing the denominator. As you can see, I no longer have a radical symbol in my denominator. And the big question was really, what can I take a fifth root of? How do I get 3 to the third? What do I multiply it by in order to be able to take a fifth root? And that was 3 squared. I needed 2 more 3's. And this is what we'll be covering, as well as what is in section 7.3 for the next class. So let me continue and work through a couple of other examples. One of the ways that I originally taught you guys to think about these problems were to go ahead and break down the numbers. So right now, I can't break down 2, but I can break down 4 into 2 squared. So I'm going to go ahead and do that. The cube root of 2 times the cube root of 2 squared. And using the product rule, that tells me that I can go ahead, since the index number is the same, they both have 3's, so we're taking the third root, I can go ahead and put these numbers right next to each other and multiply them. So I'm going to have 2 times 2 squared, which is cube root of 2 cubed, and since it's the third root, if I decide to rearrange it in the exponential form, that means I'm taking 2 to the third to the 1/3 power. That's what the third root is. And then that's 2 to the third times 1/3, which that reduces to 2 to the 3 over 3, which is 2 to the first, which is just 2. So 2 is your solution. Another example. So what if I have a division problem? I know from what we just covered, I don't want that radical in the denominator. Let's see if instead of having to do that complicated process of rationalizing the denominator, we might be able to use the quotient rule. Well, check. Alright, the index number is the same, so that means I can put it all under one big radical, keeping my division. So 81 divided by 3. Can I do 81 divided by 3? You absolutely can. 81 divided by 3 is 27. And let's go ahead and see what 27 factors into. That's 3 to the third. So if I have the cube root of 3 to the third, those powers cancel out because that is a 1/3 if I decide to write it out. 3 to the third to the 1/3, that becomes equal to 3. 3 is your solution for this one. And let's look at a difficult problem. I believe this is number 26 on your packet that we worked out together in class. I do want you guys to keep in mind that the index number right here, it is odd, and on the first problem it is odd. If it is even, an even index number means that when you are actually performing this action, when you are taking the third root, if it happened to be the square root or the fourth root, do not forget your plus or minus, because you're going to end up with 2 solutions. Alright, going back to the difficult problem, number 26. We worked this out in class, and I flew through it, and we barely got to the end by the time the bell rang. So let's see what we can remember. Alright, when I take the third root of something, I want to, once I'm able to take the third root of something, I'm going to be putting it out front because it's still going to be multiplied. So that's just one thing I want you to keep in mind. So right now, I want to go ahead and break down 64. 64 into its factors, 2 and 32, and 2 and 16, so on and so forth. This is 2 to the 6th. Alright, so that means that if I use the product rule, I can go ahead and break 64 x to the third and y apart into their separate cube roots. So I have 2 to the 6th, and then I have the third root times the third root of x to the third times the third root of y. And then I will handle my denominator in a minute. Okay, so if I look strictly at 2 to the 6th, the third root of 2 to the 6th, that is 2 to the 6th to the 1/3, if I decide to make it a fractional exponent, and 2 to the 6 over 3, which is 2 squared. So that means when I'm actually performing this root and reducing the exponents, it becomes 2 squared, which is just 4. I'm just going to write 4 for now. Alright, and the third root of x to the third is just x, and I can't take the third root of 1y by itself. So, now looking at the denominator, there's a couple things that should come into mind. That negative exponent. That negative exponent means that it's going to move from the denominator to the numerator, or if you decide to think of it as a division problem, this is x to the first. Since I'm dividing, I'm going to take x to the first minus that x to the negative third, so that's going to become x to the fourth on top. If you decided to move that x third because of the negative exponent, it would have been multiplied by x cubed times x, so you're going to end up with x to the fourth on top, and as you're able to see, the 4's, 4 divided by 4 is just going to be 1. Alright, so I took care of those x's, and then I have the third root of y over y. And the last question I want to ask myself is, alright, everything is reduced, the numbers dropped out, I don't have negative exponents, and is there a radical sign in the denominator? No, there is not. We are all good. That should be our answer. Please email me if you guys have questions. The biggest part of this was dealing with the negative exponents and rationalizing the denominator, which was a little bit of a newer piece of information. Alright, see you guys tomorrow.